Good day, everyone! Hello, grade 9 learners! Welcome back to Radio Z-eskwela. I am your Science 9 teacher on air. I am 𝗏𝗵𝗲𝗃. Welcome to another learning episode in Science 9. Please prepare your paper, pen, and module. Our lesson for today is about quantum mechanical model of an atom. This module is divided into two lessons. Lesson 1, Electrons and Energy Level. Lesson 2, Electron Configuration. In your previous grade, you learned about Rutherford's atomic theory. According to this theory, an atom is empty space, and its mass is concentrated in a small region at the center called nucleus. The protons and neutrons are located inside the nucleus, while the electrons are distributed around the nucleus. However, this model could not explain the characteristic color of flame emitted by metals when heated. In this module, you will learn about Niels Bohr's atomic model. Furthermore, you will gain understanding about the quantum mechanical model of an atom. This is important so that you will understand that the characteristics of matter are related to how electrons are distributed inside the atoms. The lessons in this module is aligned on the learning competency, explain how quantum mechanical model of an atom describes the energies and positions of the electrons. Before we will go to our discussion, we will try to find out first how much you already know about quantum mechanical model. Just try and do not worry about mistakes. I will read the question twice and you have to choose the letter of the answer from among the given choices. So are you ready? Then let's start. Number 1. What does the flame test prove about the inner structure of an atom? What does the flame test prove about the inner structure of an atom? Letter A. The atom has a nucleus. Letter B. The nucleus is positively charged. Letter C. The electrons are found outside the nucleus. Letter D. The electrons carry discrete or fixed energy. The answer is letter D. The electrons carry discrete or fixed energy. Number 2. What happens to the energy of an electron as it goes farther from the nucleus? What happens to the energy of an electron as it goes farther from the nucleus? Letter A. Its energy increases. Letter B. Its energy decreases. Letter C. Its energy becomes fixed. Letter D. Its energy does not change. Correct answer is A. Its energy increases. Number 3. Copper chloride, when heated, emits blue light. What is the origin of this blue light? Copper chloride, when heated, emits blue light. What is the origin of this blue light? Letter A. The nucleus radiates energy. Letter B. The electron loses energy as it moves around the nucleus. Letter C. The electron absorbs energy as it jumps to a higher energy level. Letter D. An excited electron loses energy as it returns to a lower energy level. Correct answer is D. An excited electron loses energy as it returns to a lower energy level. Number 4. Which of the following energy levels can accommodate a maximum of 18 electrons? Which of the following energy levels can accommodate a maximum of 18 electrons? Letter A, first energy level. Letter B, second energy level. Letter C, third energy level. Letter D, fourth energy level. Correct answer is C, third energy level. Number 5. An atom with 32 electrons has blank energy level. An atom with 32 electrons has blank energy levels. Letter A, 1. Letter B, 2. Letter C, 3. Letter D, 4. The correct answer is D, 4. Number 6. How many sublevels are there in L energy level? How many sublevels are there in L energy level? Letter A, 1. Letter B, 2. Letter C, 3. Letter D, 4. The correct answer is B, 2. Number 7. How many atomic orbitals are in p sublevel? How many atomic orbitals are there in p sublevel? Letter A, 1. Letter B, 2. Letter C, 3. Letter D, 4. Correct answer is C, 3. Number 8. How many electrons can the d orbital holds? How many electrons can the d orbital holds? Letter A, 2. Letter B, 6. Letter C, 10. Letter D, 14. The correct answer is C, 10. Number 9. Which of the given atomic orbitals is of higher energy? Which of the given atomic orbitals is of higher energy? Letter A, 1s. Letter B, 2s. Letter C, 2p. Letter D, 3p. Correct answer is D, 3p. Number 10. Which is the electron configuration of oxygen which has 8 electrons? Which is the electron configuration of oxygen which has 8 electrons? Letter A, 1s2, 2s2, 2p6. Letter B, 1s2, 2s2, 2p4. Letter C, 1s2, 2s3, 2p3. Letter D, 1s2, 2s2, 2p3. Correct answer is B, 1s2, 2s2, 2p4. Alright, I hope you have now an idea on what will be our topic today. You will learn more about it as we go on with our lesson. At the end of the lessons in this module, you will be expected to relate the colors of light emitted by metals to the structure of the atoms. Infer that the electrons can stay only in definite levels. Identify the energy levels, sublevels, and atomic orbitals in an atom. Determine the maximum number of electrons that can stay only in an energy level. Determine the pattern of filling the atomic orbitals based on the given electron distribution of the first 10 elements, and write the electron configuration of the elements in the third period of the periodic table. When we return, we will discuss the lesson 1 in this module. Stay tuned, grade 9. Have fun learning!
The Radyo Z-eskwela program of the Division of 𝗣𝗿𝗵𝗵𝗲𝗍 is being brought to you by 𝗦𝗵𝗲𝗵𝗵𝗵𝗲 Builders Construction and Supply Incorporated, Maverick Builders Incorporated, Mitch Construction and Supply, Archicons Architectural Construction and Supply, DB Construction and Supply, Hanaway Builders Corporation, Phoenix Curvada Tagum Gasoline Station, Master Construction and Supplies, Mackenzie Builders, GP&H Construction Incorporated, Metro Gear Construction Corporation, NEN Builders and Development Services Corporation, Max Mays Enterprises Incorporated, We Inc. Construction Company, Rangay Construction and Supply, East Sussex Enterprise, WM Construction, Councilor Boogie and Miss Marjorie Vertodazo, Icon Builders and Supply, and Apex Mining Company Incorporated.
Welcome back to Science 9. Now, let's have the lesson 1 in this module. A striking display of fireworks is done all over the world during New Year's Eve. Have you observed the different colors of light emitted by this firework? Do you know what is responsible for this array of colors? Would you believe that this is due to the arrangement of electrons within the atoms? Firework effects are produced by combustion of explosive materials present in fireworks. These explosive materials are also called metal salts. Metal salts emit characteristic color of light when heated. Some examples of these are shown in Table 1, page 4 in your module. In a color spectrum, each color of light has specific wavelength. Among the visible light, red color has the longest wavelength and has the lowest energy. Violet light has the shortest wavelength and has the highest energy. When compounds of different elements are heated over a flame, it comes to a point where the hot gaseous atom begins to emit light to a definite color. Analysis of light given off by the vapors of elements can be done more precisely with an instrument called spectroscope. With the use of a spectroscope, one can detect a series of narrow lines or line spectrum on the light given off by an element. The spectral lines suggest different energy levels in an atom. How did Niels Bohr explain the spectral lines of an element shown in the spectroscope? Before we will discuss the answer, let us know first who is Niels Bohr. Niels Bohr, or Niels Henrik David Bohr, was born October 7, 1885 at Copenhagen, Denmark. He was the first to apply the quantum concept, which restricts the energy of a system to a certain discrete values, to the problem of atomic and molecular structure. He is known for his Bohr model. Now let's go back to the question. How did Niels Bohr explain the spectral lines of the elements shown in the spectroscope? He explained that each line in the atomic spectra of elements suggests definite energy transformation within the atom. According to him, the electrons are moving around the nucleus in circular path or orbit at definite distances from the nucleus. What exactly are these paths or orbits in which electrons revolve around? Let us understand with an example. In the solar system, The Sun is stationary at the center, while the planets revolve around it. And no planets is jumping to another different path or orbits all of the sudden. The planets always encircle the Sun in defined or same path. In similar way, in the atomic structure, the nucleus acts like the Sun. It is located at the center. And the electrons are like planets that are revolving in a fixed defined orbitals. These orbitals are called shells or energy level. This atomic structure is also known as planetary model. Electrons in each orbit have definite energy. This energy increases as the distance of the orbit from the nucleus increases. And how to name the shells to indicate their positions? It's simple. Beginning from the shell near the nucleus, we name that as K shell, L shell, M shell, and N shell. And we can also assign them in number. Just add lowercase or small letter n and write them as n is equal to 1, n is equal to 2, n is equal to 3, and n is equal to 4, beginning again at the nucleus. Niels Bohr proposed that the electrons revolve around the nucleus with specific orbital, and this orbital comes with definite energies. The maximum number of electrons that can be accommodated in a particular orbit is 2n to the power of 2, where n is the number of orbits. Thus, for example, K shell has 2 electrons. How do we get this? For the K shell, we have n is equal to 1, because K shell is in orbit 1. In that, we have 2 times 1 raised to the power of 2 is equal to 2. So the maximum number of electrons per shell or energy level are as follows. For K shell, we have 2 electrons, L shell, 8 electrons, M shell, 18 electrons, and N shell, 32 electrons. The Bohr atomic model states that energy increases as the distance of the orbit from the nucleus also increases. As long as the electron stays in its given orbit, there is no absorption or emission of energy. If the electron receives extra energy, it can jump into a higher energy level. This is called excited state. The electron in the excited state can return to its original lower energy level or ground state by releasing discrete amount of energy in the form of light. But since Bohr's atomic model can only describe atomic spectrum of an atom having only one electron like that of hydrogen, an Austrian physicist, Erwin Schrödinger, together with Werner Heisenberg and Louis de Broglie, made a refinement of Bohr's atomic model. Schrödinger used mathematical equation to describe the possibility of finding an electron in a certain location. This model is known as the quantum mechanical model of the atom. Based on the quantum mechanical model, it would be impossible to plot a definite path or orbit of the moving electrons. We can only guess the most probable location of the electron in each instant to be within a certain volume or region of space surrounding the nucleus. An atomic orbital is the region around the nucleus where the electron is mostly likely to be found. The atomic orbital serves as the house of the electron. it can accommodate a maximum of 2 electrons. Tracking down the location of a given electron in an atom is similar to tracking where a person lives. To find this person, you need to know his complete home address, city, barangay, and house number. This corresponds to the energy levels, sublevels, and atomic orbitals in an atom. In order to track where all the electrons in an atom are, chemists use notation called electron configuration. The Table 1 in page 11 shows the distribution of electrons in the atomic orbitals of the first 10 elements. In the electron configuration 1s2, 1 refers to the main energy level occupied by the electron. S denotes the kind of orbital, in the superscript 2 for the number of electrons in the orbital. The main energy level also tells us the same numbers of the sublevels. In the name of the sublevel is also the same with the name of the orbital. 3 rules are applied in deriving the electron configuration. First, we have the 𝗏𝗏𝗶𝗃 principle, the Pauli exclusion principle, and the Hus Rule of Multiplicity. 𝗏𝗏𝗶𝗃 principle, it is also known as the building up principle, states that electrons must first occupy the orbitals with lower energies than those with higher energies. It follows this mnemonic and filling up the orbitals. The first orbital that is assigned 2 electrons is the 1s, followed by 2 electrons for 2s, and another 2 electrons for each 2p orbital for a total of 6 electrons for p sub x, p sub y, and p sub z. This sequence goes on until all the electrons in an atom have been assigned to orbitals. Note that the maximum number of electrons in s orbital is 2, p orbital 6, d orbital is 10, and in f orbital is 14. Let's try writing the electron configuration of lithium, which has 3 electrons. We will have this electron configuration: 1s2, 2s1. Another example is sodium, which has 11 electrons. Its electron configuration is 1s2, 2s2, 2p6, and 3s1. Now we're done with the first rule. Let's move on to the next rule, the Pauli's exclusion principle. According to Pauli's exclusion principle, only a maximum of 2 electrons can occupy an orbital, and they must have opposite spins to minimize repulsion between them. To give you a better idea, consider again lithium, which has 3 electrons, as an example. Its electron configuration is 1s2 and 2s1. Its orbital diagram looks like this, and not like this. This is because, according to Pauli, electrons occupying the same orbital must have opposite spin to minimize repulsion. Now, let's proceed to the last rule, the Hus Rule of Multiplicity. According to this rule, when electrons enter a sublevel with more than 1 orbital, they will spread out to the available orbitals with the same spin before pairing. To better understand this, let's have the following example. Consider nitrogen, which has 7 electrons. Its electron configuration is 1s2, 2s2, and 2p3. Its orbital diagram looks like this. As you can observe, the electrons in the p orbital have spread out first to the available orbital with the same spin before pairing. To have a better understanding with our topic, practice on the different exercises found in your module. When we return, we will have a short recap and a short quiz. Welcome back, learners! Are you ready now with our assessment? Very good! But before that, let's have first a short recap. We learned that Bohr's atomic model describes the atoms like a solar system, where the electron is found only in specific circular paths or orbits around the nucleus. Electrons in each orbit has fixed energy. An electron can jump to a higher energy level by gaining energy and return to a lower energy level by releasing energy in the form of light. The Bohr model was later replaced by a model of the atom that showed that the electrons are not limited to fixed orbit around the nucleus. Schrödinger formulated a mathematical equation that described the behavior of the electrons. The solution to the equation was used to calculate the probability of finding the electrons at a particular region in space around the nucleus. It is then called atomic orbital. The quantum mechanical model describes the atom as having a nucleus at the center and around which the electrons move. This model describes a region in space where the electron is mostly likely to be found. The distribution of electrons in the different atomic orbitals is called electron configuration. Good remembering, learners! Let us now determine how much you have learned from the lessons and activities. Listen carefully and choose the letter of the best answer from the choices. Write your answer on your paper. Are you ready? Very good. Number 1. Which statement below supports the Bohr's model of the atom? Which statement below supports the Bohr's model of the atom? Letter A. The model was accounted for the absorption spectra but not for the emission spectra. Letter B. The model was accounted for describing the electron to be moving in definite orbits around the nucleus. Letter C. The model was based on the wave properties of electron. Letter D. The model accounted for the emission spectra of atoms but not for the absorption spectra. Number 2. Which orbital designation has the highest energy? Letter A, 2p. Letter B, 3p. Letter C, 3d. Letter D, 4s. Number 3. What happens when an electron jumps from higher to lower energy level? What happens when electron jumps from higher to lower energy level? Letter A. Colored light is given off. Letter B. The atom becomes excited. Letter C. Another electron goes from a low energy level to a high one. Letter D. This process is not possible. Number 4. Who among the scientists did not contribute to the development of the quantum mechanical model of the atom? Who among the scientists did not contribute to the development of the quantum mechanical model of the atom? Letter A. Werner Carl Heisenberg. Letter B. Louis de Broglie. Letter C. Erwin Schrödinger. Letter D. Niels Bohr. Number 5. How many electrons can each p orbital hold? How many electrons can p orbital hold? Letter A, 1. Letter B, 2. Letter C, 3. And letter D, 6. Are you done with our assessment? Great! Please continue answering the activities in your module. If you have questions and clarifications, write it in a piece of paper and include it in your output envelope. I hope you learned something today. This is again Ma'am Sheila, and together with Sir 𝗦𝗵𝗲𝗵𝗵, thank you for listening. Until next time, God bless and keep safe always.
𝗏𝗃eskwela Executive Committee. The School's Division Superintendent, 𝗦𝗵𝗲𝗵𝗵𝗲 5. Assistant Schools Division Superintendent, Dr. 𝗦𝗵𝗲𝗵𝗵𝗵. OIC Curriculum Implementation Division Chief, Karina S. Frasco. School Governance and Operations Division Chief, Dr. Ruben J. Riponte. Members: Cecilia Morales, Dr. Hilda A. Opeña, Dr. Arlene B. Lim, Dr. 𝗣𝗿𝗵𝗲 B. Calzadora, Dr. Dexter A. Siquinha, Nohara O. Pinute, Noemi P. Canales, Dr. Grace D. Pontillas, Virgilito C. Pabrices, Juanito Lapiceros, Engineer Norberto S. Manlangi, Jomar M. Dumupoy, Bob Dalan S. Milabat, Medard T. Ampit, and Paz Eugenia Villusino. Technical Working Committee, Productions and Communications, Lorely E. Quijano, Given G. Hinampas, Judyland D. Yu, Donna D. Bolfer, Mary Rose N. Resma, Riven Manuel, Irene Lea C. Manguhon, and Bessie Aya N. Banias. Social Media and Packaging Team, Christian and Hara L. Martesio, William R. Ranara, Joan T. Iscoton, Roberto S. Acusar Jr., May B. Istanyol, Richard H. Arellano, Lee L. S. Blanco, Ralph A. Tabanyag, Angelo Gutierrez Jr., and Jade Karen Araiz.